NASA's Europa Clipper spacecraft will explore Jupiter's icy moon Europa. The spacecraft is outfitted with sophisticated tools to investigate a vast ocean beneath the moon's surface and to determine if it can support life. With the launch date approaching, SWRI space scientists join us to discuss the journey to the Jovian satellite and the instruments their teams designed and built for the extraordinary mission. That's next on this episode of Technology Today. We live with technology, science, engineering, and the results of innovative research every day. Now, let's understand it better. You're listening to the Technology Today podcast, presented by Southwest Research Institute. From deep sea to deep space, we develop solutions to benefit humankind. Transcript and photos for this episode and all episodes are available at podcast.swri.org. Share the podcast and hit that subscribe button on your favorite podcast platform. Hello and welcome to Technology Today. I'm Lisa Benia. NASA's Europa Clipper spacecraft will launch next month. The launch window opens October 10th. The mission's purpose is to collect data and images to examine a vast saltwater ocean beneath the surface of Jupiter's icy moon Europa to determine if it contains the ingredients to support life. If Europa can support life, then there could be life elsewhere in our solar system. 2 SWRI instruments will make the journey to Europa. Our guests today are SWRI space scientist Dr. Jim Birch, who leads SWRI's space sector and is the principal investigator of Clipper's mass spectrometer for planetary exploration, or MASSPEX, and Dr. Kurt Rutherford, space science senior program manager and principal investigator of the spacecraft's ultraviolet spectrograph, or Europa UVS. Thank you both for being here, Jim and Kurt.
Thanks, Lisa. Happy to be here.
As we just mentioned, the Europa Clipper launch window opens October 10th, so we want to hear about how you're preparing for the big day. But let's start with an overview of NASA's Europa Clipper mission. What is the purpose or goal of the mission?
Overall, we're looking to learn more about Europa's habitability. That's a loaded word to not say that we're going to go search for life, but that's really what we are hoping to do eventually in space exploration. But what this means is, does it have the ingredients for life? Does it have water? We're pretty sure it has a liquid water ocean. Does it have stuff for bugs or people to eat, basically, the raw elements? And then is there the energy to keep those materials coming to sustain life in this environment? And that's what habitability means.
Can you tell us about this ocean, this vast ocean that scientists believe lies beneath the surface?
Yeah, this ocean was detected on a previous mission, Galileo, by magnetic field measurements. And Europa Clipper will also make magnetic field measurements to confirm and learn more about this ocean. It gives magnetic signals because there's salinity in this water, like salt water, as you said. And as the planet rotates, there are eddy currents that build up, and these create magnetic fields. So we know there's an ocean subsurface. The question is, can it support life? And so there are various different instruments. There are imagers that look in various wavelengths, ultraviolet, like Kurt, is infrared, visible. There's a dust detector. There's a radar that probes the structure of the moon. And then there's MASSPEX, which looks for organic compounds. And as Kurt said, you also have to have a source of energy. It can't be sunlight like on Earth because the moon is under the surface. It has to be chemical energy from chemical reactions. So MASSPEX also looks for products of those chemical reactions. So with this, we can determine, is there organic compounds? Is there a source of energy? We know there's water. Well, those are the requirements for life. So then we could say, is it habitable or not? We're not looking for life. That would be another mission with other instruments, but is it habitable? And so we've worked a lot on trying to make these measurements, and it turns out previous measurements can't do the job here, at least in mass spectrometry. And we had to advance the state of the art in terms of mass resolution by a factor of 50 over anything flown previously. So it was a major undertaking.
So tell me about those images from Galileo that first clued you in on this ocean. What were the signs? What was the evidence there that there...
It was not images. It was magnetic field signals. So you see these signals, and people model, what you would get, where they would come from, and what a ocean that had, minerals in it like salt, what type of currents and magnetic field signatures would they produce. And this is well known. And there are other moons in the solar system that also have these subsurface oceans, like Ganymede at Jupiter and Enceladus at Saturn. Similar things.
I'll add that Jupiter has one of the strongest magnetic fields in the solar system. If you could see it with your naked eye, it would be bigger than the full moon, even as far away as Jupiter is. And Jupiter rotates around. That dipole is a little bit tilted. So as that tilt goes past Europa and changes with time, we could see that changing current within the ocean that gets induced by that magnetic field moving around through that conductive medium that Jim described. So the magnetometer was very sensitive to that and picked it up really well. And there are some interesting features on the surface that we call chaos regions that show that there could be some sort of icebergs kind of flipping over on each other perhaps, or other kind of interesting hints at things and other gravity data. But it's really the magnetometer data that really pulls it all together, as there's probably twice as much liquid water underneath the icy shell of Europa as we have here on Earth. And Europa is about the size of our own moon, a little bit smaller. But just imagine all the life you see when you go to Port Aransas and put your feet in the water and see what's in the ocean there. What's in Europa's ocean? That's what our mission's really about.
All right, we want to go stick our feet in Europa's ocean and check it out, get to know more about it. What's in there? So we know the spacecraft launches next month, but it won't actually arrive into Jupiter's orbit until 2030. I mean, that is an epic journey, and that's going to take some time. So what distance are we talking about here?
So Jupiter is pretty far away. You could rattle off the names of the planets in the solar system, but basically, when you think about the distance between Earth and Sun, it's 5.2 times as far away from the Sun as Earth is. So that's the best way to get a feel for how far away Jupiter is. And it's going to take us about 6.5 years after we launch on a big Falcon Heavy rocket to get there. And I'll say that big rocket is fast in terms of solar system exploration speeds. So long-term gratification, but we're happy with that tour.
We use some gravity assists from Mars and from Earth to speed this path up. If you had a big enough rocket, you wouldn't have to do that, but we have to get some gravity assist by swing by of Mars and a swing by of Earth. And by comparison, the European mission to Jupiter, we're also mainly focusing on Ganymede, has already been launched over a year ago, but it won't get to Jupiter's orbit until after Clipper, because it has a different strategy. And so this is a pretty fast way of getting there with this Mars and Earth gravity assist. Even though 6 years sounds like a long time, it's actually pretty fast.
All right. When we're talking about this, as you said, planetary exploration, 6.5 years is a speedy way to get there, speedy timeline. Yeah. We've touched on this a little bit already, but why is there interest in exploring Europa specifically? Why not other moons or other places? What makes it an ideal target for this type of exploration?
It's an excellent question. There's another ideal target, and maybe even more ideal, Enceladus at Saturn, but it's twice as far away, much more difficult, and eventually we'll do that. So Europa's closer, relatively, and it's a very interesting moon. Another moon that's also interesting is Ganymede, as I mentioned, and the European mission is mostly going to investigate that, but not with instruments like we have on Clipper. So the Clipper 1 and Europa will be unique. The challenge is that it's in a very high radiation environment around Jupiter of trapped radiation, and so that's a challenge, but we're designed to survive that. All of our electronics, or most of it, is put into a vault that shields out that radiation.
And we've done that before.
We had a vault similar to that on Juno, which SWRI led, the Jupiter mission, but it was in a polar orbit, so much less radiation dose, but still significant, so that it had this type of vault.
Well, a good test run, at least, for
Yes.
Europa.
And I'll add Enceladus, the moon around Saturn that Jim described. That's about the size of Texas, or a little bit bigger, whereas Europa is about the size of the moon, Earth's moon. So there's more water on Europa, we think, overall, and maybe a better chance for some evolution of life there is what some astrobiologists think, at least. And while we know from the Cassini mission that Enceladus has water geysers shooting way out from its surface, we had Hubble Space Telescope observations led by my postdoc that discovered geysers on Europa as well. So with Europa Clipper, we're really interested in understanding whether there are these plumes of water vapor coming off of Europa, maybe out of cracks and vents that lead to the subsurface in some way. And then what's the composition of that vapor that's coming out of the surface, and how do we measure that the best way?
So if Europa holds the essential building blocks for life, like carbon, hydrogen, oxygen, sulfur, what does this tell us about the potential for life elsewhere in the solar system?
Just that since Europa, like some other moons, has these subsurface oceans, if Europa has the proper building blocks for life, then it increases the likelihood that these other moons also will have those. But we have to go there to find out. But it would be a good indicator that there's life elsewhere in other subsurface oceans.
So if you find the ingredients for life on Europa, the thought is that could exist elsewhere in the solar system on these other moons, other places.
After the Galileo mission found this evidence for water on Europa underneath its icy shell, we started to realize that there are a lot of what we now call ocean worlds in the solar system. Maybe even Pluto and its moon have subsurface oceans deep down inside of them. And so it's a real fascinating sort of paradigm change in terms of how we think about exploring the solar system. Where are these niches where life could exist? Are they habitable? How did they form and how are they sustained? It's sort of a mind-changing perspective on things. Where did we come from? What's the origin of life here on Earth? Does that process happen elsewhere in the solar system or the universe more broadly? These are the big questions in life that we're answering as scientists, and that's, I pinch myself thinking that I get to work on this type of thing when I come into work.
Yeah, huge. Okay, so we've mentioned the instruments a couple of times, but I really want to get into it now. So, what is SWRI's role in this mission?
So of the 9 instruments on Europa Clipper, SWRI has developed 2 of them, which we're very proud of. And one that I'm responsible for is a mass specs. It's very simple in principle. Most people know energy is equal to 1/2 mass times the velocity squared.
I think I remember that formula.
Okay, so we bring gas in and we ionize it with a little filament, a little small electron beam. We ionize the gas, and then we accelerate all of the molecules and atoms up to the same energy, 300 electron volts. They all have that same energy. So we know E. We want to find M, the mass. So what we need to find is V, the velocity. And so with this, we have a device that's just a straight-through device, 1 meter long. And so that's our baseline. So if we measure all of the atoms and molecules that come in time, how long does it take them to get from one end to the other? Then that gives us their velocity. The trouble is that's very low resolution on 1 meter. So we trap these atoms and molecules in this. We call it a multi-bounce time of flight. We trap it with electrostatic mirrors, and we go up to 800 round trips. So we go from a 1 meter baseline to a baseline that's almost a kilometer. And with that, things start separating out so that we get mass resolution 50 times better than anything flown in space before. And the way we measure it is mass divided by the width of a mass peak, and that gets up to 50,000 in mass specs. 1,000 is the best that's ever been done, and this was on the Comet mission, Rosetta. So we know we're going to get a mass spectrum much finer than anybody's done before. And if there are organic molecules or products of chemical reactions that we're looking for, we will find it.
So does it tell you what you found? Does it label its findings, or can you?
Well, we know the mass, and once you know the mass that accurately, you can pin it down to a certain molecule.
Knowing the mass is knowing what it is.
Yes.
Okay, so Jim, again, you're the principal investigator of the mass spectrometer for planetary exploration, also known as MASSPEX, as you mentioned. And so what is its, you just explained its process, how it works, and how is it going to contribute to the overall mission? What is its role in the big picture?
I think it's a central role because you have to have liquid water for life. We know that. Next thing is organic molecules. That's what we find. And then the other is a source of energy. That's these products of chemical reactions, and we will find that also. So in that sense, MASSPEX could do the whole job, but we have to have something to look at. And then what we can look at is a very thin atmosphere of Europa. And this can be coming out of sputtering by energetic particles or other types of other fissures, and also these plumes that were discovered earlier by Kurt. If we could fly through a plume, that would be great because we would know it's coming from the ocean. So what we want to do is sample the material from the ocean. And once we do that, then we really accomplish everything in terms of habitability.
So I'm trying to get a picture of how this plays out. And, I'm thinking of the spacecraft flying, doing orbits around the moon, but just clarify. So will it land on the surface?
Okay, it's not in orbit around the moon. The spacecraft is in orbit around Jupiter, and we have up to 50 flybys, maybe a few less, of the moon, very close flybys. And
but enough to scoop some of it up?
And we don't land,
no.
And we don't scoop.
Okay, no landing, no scooping.
Just close flybys.
You could call it sniffing.
Sniffing, yep.
Okay. That helps because I thought it was just hovering but then I wasn't sure if there was actual contact made with the moon. But okay. What will the findings of MASSPEX tell us about the habitability of Europa?
Well, it tells us, are there organic molecules of the type that we see in life? And is there an energy source? The other thing it has to be an environment that's stable over time for life to develop. It can't be changing. Now, we can't answer that question, but we can answer, is there an energy source and are there organic molecules?
And Kurt, I want to talk about SWRI's second instrument on CLIPPER. So Europa CLIPPER's ultraviolet spectrograph. Tell us about this instrument. What is its function?
So I'm excited about ultraviolet light because a lot of the basic transitions of atoms and molecules happen at the wavelengths that our instrument's really sensitive to in this range. Just if you think about that first excited state of an electron orbiting around a hydrogen atom, and when it drops down and gives off a photon, that photon of light falls in our wavelength range that we measure. So we can study hydrogen atoms really well. We can study oxygen atoms really well. And what we did with Hubble was watching water molecules break up into those hydrogen and oxygen atoms and having those excitations that gave off photons at these wavelengths that we're able to see at ultraviolet light coming through our telescopes like Hubble or Europa EVS. And so what we're interested in is this auroral emission, when an electron busts up that water, how it glows, and whether there is a plume of gas in a given location, or just understanding water and oxygen and other atoms in Europa's exosphere, like Jim was describing earlier, more basically.
So I was reading about these plumes that UVS is going to be hunting for. So how does it hunt for these plumes from Europa's surface, and what does it tell us about the plumes?
Great. Yeah, we have a telescope part of our instrument, and then light passes through a narrow slit onto a grating that breaks it up like a prism into its constituent wavelengths of light that map onto our detector, much like the digital images that you get on your cell phone. So we'll get digital images of a spectrum of light passing through that slit. And when we scan that slit across the circle of Europa, we'll get an image of Europa at all of its different wavelengths of light. So we'll get hydrogen glow images, oxygen glow images, put those two together and sift apart how much of that's from atoms versus water molecules and all sorts of other tricks that we can play. So we'll be looking at Europa more globally to find out where these plumes may be. We still need to get more conclusive evidence of these plumes, following up on our Hubble and other observations folks have followed up on. But once we find out where these are, and then the Europa Clipper spacecraft flies through them and mass spec sniffs them out, putting these two measurements together, we'll have a real powerful set of data for us to really understand what Europa's atmosphere and these plumes are made of compositionally. And certainly the composition of atoms and molecules we see at UV wavelengths isn't nearly as telling as the mass specs instruments will be in terms of more complex organics and interesting molecules. But we will be able to piece together some compositional information as well across Europa's surface in different locations. And I will add on, I believe the mass specs instrument that we're doing here is one of the most powerful tools for doing this astrobiology, is what we call it, this studies of habitability and life in the solar system. So I'm really excited about the mission overall and how all these instruments are going to work together to pull this off.
Yeah, again, 9 instruments, SWRI leading up 2 of them, really important to the mission as a whole. You know, we talked about the radiation case around Clipper, but when talking about mass specs and the UVS instrument, has the technology for these 2 instruments been used before for other missions, or were they developed specifically for Europa Clipper?
Let me say, Jim described nicely the European Space Agency's mission to the Jupiter system. It will eventually orbit around Ganymede, and that mission is called JUICE, the Jupiter Icy Moons Explorer mission. And we have an almost identical instrument on it for this UV spectrograph UVS instrument that we call JUICE UVS. And it was really exciting to watch that launch a year and a half ago or so. Just the other day, it flew by the Earth and Moon, getting its gravity assist along its way. And its trajectory gets there 8 years later. And we're already starting to think of how do we put these 2 instruments to work to observe Europa and Ganymede all at the same time and leverage the science from both these instruments. SWRI has contributed on that front.
So existed before, but definitely building on it for this next mission.
Yeah, and so Europa UVS is the 6th in the series. Before Europa was JUICE. Before JUICE was the Juno UV spectrograph that's still in orbit and doing great science there. Before that was the Lunar Reconnaissance Orbiter Lyman Alpha Mapping Project instrument that I'm also the PI of. And then before that was New Horizons, Pluto Alice, and Rosetta Alice. So a long series of 6 instruments, and we're looking forward to doing more of those as well.
Mass specs, as I mentioned, is a multi-bounce time-of-flight mass spectrometer. And a device like this was flown on the European Rosetta mission to Comet, but with mass resolution 50 times coarser than what we do with mass specs. So mass specs is a type of instrument that's been flown before, but nothing has come close to it in terms of mass resolution. So we hope that we can fly it many other places in the future.
The new and improved, most cutting-edge version.
Right.
Okay, so I want to talk about launch day. The window opens October 10th, definitely an exciting time for everybody on the team. So what preparations are taking place before that launch window opens?
Spacecraft's been delivered out to Cape, and they're doing some testing. Hopefully we'll get our instrument turned on here pretty soon to make sure it's working, but it won't be turned on fully. There are just some abbreviated tests right now because everything has been tested very completely back at JPL. So now, we're just things. I think the next milestone coming up is fueling the spacecraft, the onboard fuel that it takes to manage these flybys of Europa. And so once that happens, then there's no going back. We're going for sure.
Are there last-minute meetings with the team or discussions? Have any last-minute challenges popped up?
Not too many. We have our meetings all the time. In fact, there's one today at noon, right, where we get updates on, how things are going. But as far as I know, everything's working fine.
Smooth sailing. Okay.
We had a little bit of a scare with a computer chip called a MOSFET from a particular vendor. So we'll hear more about that in the days coming up to launch. But looking at that very carefully, but so far so good.
And those are just the little things you work out before you get to the launch date. Yeah.
Yeah.
Business as usual. Okay, so I wanted to talk about you each personally. What has been your experience planning for launch? I mean, this is years in the making. So how are you each getting ready for the big day?
Well, let me go back and say this computer chip issue isn't like business as usual.
Oh, it's not. Okay.
This is
easy for me to say, right?
all hands on deck, Tiger team studies. Let's look at this, study it and some more, and study it again. And lots of decisions going on at NASA headquarters on this topic still. But no guts, no glory in this business for sure. We're going for the big science, and that's what it's about.
The big science.
Yeah.
And so as you're working out this little issue, anything else coming up for you that you're focusing on?
Certainly all the preparations to try to get all the tickets to the launch site and get our friends and families involved. That's all going on right now. And we're definitely looking forward to having a project science group meeting amongst all the scientists the week before October 10th, just to really talk about the science we're going to do, get ready for launching, and there'll be some more public outreach activities going on as well in the lead up.
We're doing a lot of planning about how to test out the instrument when we first turn it on, and then how to operate it. Once we get to Europa, we have a very detailed plan for how to operate the instrument, and we're doing that, working all that out right now.
And where will you be on launch day? You'll be right there at the launch site?
We're sitting in the bleachers at a place called Banana Creek. It's like the closest place you can be, and so I think that's where we'll be watching it. It's a high noon launch, so have our sunscreen and wait. I mean, you don't have to wait. It either goes or it doesn't.
Yeah.
And then there'll be, try the next day. And the thing that could make that happen mainly is weather. I think October 10th, well, that's still hurricane season, right? So don't know about the weather.
Yeah, so how long is that window open?
It's open to about 4 weeks.
Oh, okay. So if it doesn't go within that little time frame around October 10th, then you'll have to go back. Is that the plan?
I think it could go the next day. It stays. I think at some point they might have to, go in and do some changes, bring it off and refuel it but I don't know what those are. As far as I know, it's just day-to-day slip.
Yeah, and after that 4-week window, there are backup plans for several months later to go get that Mars flyby gravity assist again. We'll have to wait for that one.
All right, so here's hoping that October 10th works and you get to see it all unfold right there before your eyes, all your years of hard work. How many years are we talking about here? When I know it's been in the planning forever, but do you have what year was that?
Yeah, I think we were writing proposals in 2014 and they were awarded in 2015. So going on 10 years here now. Yeah.
It's finally coming to fruition. So that's got to feel good. What does the mission mean for you and your team?
For me, this is one of the pinnacles of my career so far, no doubt. Certainly the team that we have here at the Institute is hands down the best set of people I could hope to work with and ever have worked with. Just everyone's so dedicated to the goals of the mission overall, the quality of the engineering that goes into it, and just the camaraderie of having this bigger goal that we're all trying to achieve. It means a lot to me.
Yeah, we calibrated our MassSpecs instrument, and calibration data were fantastic. We got really excited looking at what it could do. Now we have to wait 6 years, but when we get that first light from that instrument and see our first mass spectrum, it's going to be very exciting. And some of the people working on it then probably could be in high school right now. We keep vitalizing our team with incoming graduate students, postdocs, and then some people retire. And so it'll be a different team. But the excitement will still be there, and once we start seeing, and we know it's going to work because we've never had any problems with this instrument, and so it's going to be fantastic. We're going to learn a lot, and we won't get rich and famous, but we might publish a lot of very interesting papers.
It will be worth the wait.
Worth the wait.
So here at SWRI, we pride ourselves on conducting research and development to benefit humanity. So what does this mission mean for all of us, for humanity, the big picture? What is the significance of the mission?
We could say that there's a place where life could develop elsewhere in the solar system. That's starting to answer one of the biggest questions that we have. about our origins.
Yeah, and in the last 20 years or so, this field of astrobiology, studying these types of things, has grown and grown in terms of its importance. Our last decadal survey for planetary science priorities, a real grassroots effort, really called out this astrobiology as the area for us to go as planetary scientists to study further. And Europa is right now in that pole position of really pushing the frontier on this topic.
Expanding the field of astrobiology and answering those big questions about our existence. So really a huge mission for all of us. So, Jim, I have you in the room right now, and I want to close with a word on SWRI's space science program. You launched our program in 1977. You've been exploring space ever since. We've done some big things since that time. So what are your thoughts on the space sector's contributions to space science over the decades?
Well, it's been mostly with space missions. We provide instruments like the UVS, MASSPEX, others, for many missions, and we've provided complete missions to NASA, generally in the areas of planetary science and heliophysics. And I believe that we've led more missions than any other organization. And this, as far as full missions, it started with the IMAGE mission, which I led. It was the first mission to image charged particles around the Earth in the Earth's magnetosphere, and then continued with New Horizons to Pluto, Juno, first polar orbiter of Jupiter, magnetospheric multiscale, which investigates a process called magnetic reconnection, which is responsible for solar flares and the aurora. It's also then the Lucy mission to the Trojan asteroids, which are at Jupiter's orbit. And then now the Punch mission, which will be the first mission to image material coming off of the sun and solar flares and coronal mass ejections and track them all the way to the Earth. Never been done. So we have, and other missions. But with these sets of missions, with SWRI principal investigators, I don't think there's another organization that has that many. And so we hope we can continue.
All right. A lot accomplished since the start, from IMAGE now to Europa. Many contributions to space science as a whole. If you want to learn more about the Europa mission, there is so much information on NASA's website. You can visit their website at Europa, that's EUROPA.nasa.gov. Again, europa.nasa.gov. It's such a comprehensive website to learn more. I've had a lot of fun. It's really interactive and gives you some great tools to learn more about the mission. I had a lot of fun exploring that website. So I want to say thank you, a big thank you to both of you, Jim and Kurt, for this exciting preview of the Europa Clipper mission to Jupiter's icy moon. Congratulations to your teams on getting your instruments mission ready, and wishing you all the best on the upcoming launch. We will be eagerly awaiting Clipper's arrival to Europa in 2030, and seriously can't wait to hear about Europa discoveries and all that your instruments capture. Such a big moment for you.
Thanks, Lisa. It's been a pleasure.
Thank you for having us.
And thank you to our listeners for learning along with us today. You can hear all Technology Today episodes and see photos and complete transcripts at podcast.swri.org. Remember to share our podcast and subscribe on your favorite podcast platform. Want to see what else we're up to? Connect with Southwest Research Institute on Facebook, Instagram, X, LinkedIn, and YouTube. Check out the Technology Today magazine at technologytoday.swri.org. And now is a great time to become an SWRI problem solver. Visit our career page at swri.jobs. Ian McKinney and Brian Ortiz are the podcast audio engineers and editors. I am producer and host Lisa Pena. Thanks for listening.